Welcome back. In this lesson, we're going to look at a different type of distribution. This kind of piggybacks off of our joint probabilities that we talked about last time, but in this lesson, we're going to be looking at the distribution of a linear combination. All right, and so as we start to kind of set this up, these are really, really useful in a lot of engineering and physics applications, as it allows us to start introducing statistics-based approaches to how we model things or how we start to compute safety factors or probability. And we have an example a little bit later that will kind of demonstrate all of this. But the basic premise of a linear combination is as follows. Okay, we have a collection of a certain number of random variables that we'll call x1 through xn, x1, x2, x3, so forth and so on, and in the same number of numerical constants that we're going to call as a1, a2, all the way out to an, so forth and so on, such that I can make a new random variable that we'll call y that is basically a1 times x1 plus a2 times x2 plus all the way out to an times xn. Or if you want to do the summation notation, that's the summation of I equals 1 to n of ai xi. Okay? For this linear combination, this is a random variable now, okay? And like all random variables, it will have an expected value, it will have a variance, and once we do some things, we can start doing probability calculations off of this guy, just like you've done with all the other distributions. You know, maybe you fit a gamma distribution to this to get the probability model. It's any number of things could happen on this. But for this linear combination, the way that we derive this and start to set this up is I can say that the expected value of y is going to be equal to the expected value of my random variable. So I'm just substituting a1, x1 plus a2, all that into here. Okay, and then if I do the algebra and apply those identities for the expected value, and if you don't remember those, go back and take a look at our expected value video several videos back, okay, and we'll kind of explain those properties again, but I'm going to assume that you know it, and we'll just kind of jump into it, that if a1 is a constant, that, well, first off, I can take the expected value of all of the individual terms, okay, so the expected value of a1, x1 becomes a term, and if a1 is a constant, it can be pulled outside. Okay, and so if I rewrite all of this, you start getting something that looks like a1 times the expected value of x1 plus a2 times the expected value of x2, and so forth and so on. And that becomes kind of our approach. All right, if I do summation notation on this, this is the sum of I equals 1 to n of ai multiplied by the expected value of xi. Okay, and this is pretty cool because this is the expected value of all of the individual random variables. Now, we didn't put any prescriptions on this saying that, oh, they all had to be the same, or they all had to be normal, or all had to be uniform. It could be anything. So x1 could be exponential, and x2 could be normal, and x3 could be uniform. This still works. Okay, so that's kind of a cool idea for coming up with how to calculate the expected value of a linear combination. All right, in a similar fashion, we can calculate the variance of this, and for our variance, we have the summation from I equals 1 to n of the summation from j equals 1 to n of my ai, aj, and then because it's two variables, remember this is like that joint probability distribution that we did. You've seen this equation before, times the covariance of x1 or xi and xj. All right, and then you do this for all of the pairs, and so you should be able to establish, you know, for any number of random variables, you know, a covariance, you know, if they are not independent, that exists between all possible sets of my random variables, x1 and x2 and x3 and all the way out to xn. So there's a lot of calculations. Now, I'm not saying that it's, you know, necessarily simple to calculate all this, but it is doable with the tools that we already have in our belt from this series. All right, so but that's the general basic formula. Now, to simplify it, okay, if the xi are independent, then the variance of y is just simply the summation of I equals 1 to n of ai squared times the variance of x. And again, that's one of those variance properties, you know, the property that came out of the same video where we talked about expected value. We did the same thing with variance. So again, if you don't remember that or a little confused, go back and watch those videos again, and that'll help you out. Okay, now, there are a couple of special cases that we can start to build on this. All right, so the first one that we want to look at is the special case where n equals 2. So I have two random variables. a1 is plus 1 and a2 is a negative 1. If I do that, then the expected value becomes the expected value of x1 minus x2. Okay, so now we've got a difference calculation that we can make, all coming out of this special linear combination. So we can start doing some math with this. And if we apply our rules to this, this becomes the expected value of x1 minus the expected value of x2. That's our difference. Okay, and then for the variance, similar fashion, okay, we take the 1, so it's a1 squared. So we would have a1 squared times the variance of x1, okay, plus a minus 1 squared times the variance of x2, because that guy was my a2 value. And remember, a constant that comes out of this gets squared, so the negative sign basically goes away on this. And so this becomes the variance of x1 plus the variance of x2. So the variance of the difference is the same as the variance of the sum of the individual random variables. It's kind of an interesting little parameter. Okay, another little factoid that we can do is if the xi are independent and normally distributed, now not necessarily the same normal distribution, but if they're all normally distributed, then that linear combination y is also going to be normally distributed. And this kind of comes out of the central limit theorem that we talked about in the last video, okay, where if I start taking large enough samples, everything tends to be normal anyway, and this has kind of got its roots in that. Now again, we'll save that for an advanced statistics class or a discussion for a later day, but for what we're doing, we'll just kind of take that as kind of a side note, interesting little fact about what it is that we're trying to do. Okay, all right, so let's try one. We'll do a little bit of a sample calculation here, okay, and I'm going to go back to my world, okay, which is statics and structures. Okay, I'm a civil engineer, structures is my thing, so I like to put this into the context, something like that. But this example has a cantilever beam that has a point load that we're going to call as x1 and a point load called x2 that are located a distance of a1 and a2 respectively from the support A. Okay, and so we're given the data that the expected value of x1 is 2 kips, and the expected value of x2 is 4 kips, and that this can have a standard deviation of 0.5 kips for number 1 and 1 kip for number 2. So there's some variance, okay? And in the real world, this is the way loads are treated, okay? And so part of the challenge of a designer is to figure out, well, how much load do I need to design for, and you know, what can I start to predict, okay? And so we're going to show you the method by which a lot of the building codes, whether it's AISC or ACI or any of the, any building code, has some sort of safety factor that has its roots these days in some sort of probability mechanism. So this is almost like a risk and reliability study that we're going to look at on this. Okay, now our linear combination is going to be the value of this moment. So if you remember, when we sum moments here, it was a1 times x1 plus a2 times x2. So that's my moment. And that takes on the form of my linear combination. So this is now my random variable y, this m naught. So just for good measure, let's walk through this and do some calculations, and let's see if we can figure out what the expected value of m naught is if x1 and x2 are independent. And we'll take the location of the load a1 as being 5 feet and a2 as being 10 feet. Okay, that there are constants, that there is no variability in that it's not going to move. Well, as we saw in the previous calculation, and the expected value of m naught is going to then be a1 times the expected value of x1 plus a2 times the expected value of x2, which is now just a plug and chug problem because you were given this expected value in this one in our data up above. And so this is 5 times 2 plus 10 times 4. Our expected value of the moment is 50 kip feet. And that would have been what you got, from a classic statics problem. No problem. No issue. The difference is now in the variance. All right, so the variance of our moment then is going to be a1 squared times the variance of x1 plus a2 squared times the variance of x2. All right, so a1 was 5, so that's going to be 25 when you square it, multiplied by the variance of 0.5 squared, so that's 0.25. Okay, plus a2 was 10 squared, and the variance of x2 was 1. And again, that's all coming from the values that we had up here for our standard deviation. Okay, again, this is sigma 1 squared, and this is sigma 2 squared, as you start to kind of look at that. Okay, and again, those are variances. Okay, so then if I do the math on this, you can find out that the variance of this calculation is 106.25 kip feet squared. Okay, and so the standard deviation of this then is just the square root of that number would be 10.31. All right, so that's my expected value and my standard deviation for this linear combination as it's set up. All right, so now we can kind of start looking at, kind of like what we did with the, the distribution of the mean in the last video. We can start kind of playing some probability games here. All right, so let's just choose a number at random. Okay, and say, okay, if x1 and x2 are normally distributed, okay, then the linear combination of them will also be normally distributed. Let's find the probability that our moment, m naught, okay, is going to be greater than 75 kip feet. Okay, so m naught is normally distributed on 50. That was my expected value, or mu, if you will, of m naught. Leaving off all my knots here. Okay, and then the variance of 106.25 kip feet squared. All right, and so that's my distribution. So we know it's normally distributed because we were given that. All right, so all we do then is we play our, like we did in our normal distributions. And again, if you're having issues with this and you don't remember it, go back and watch the video. We've covered this a couple of videos back about the normal distribution. This is one of the most important ones. But let's just plug in and do our shift in variables and go from x to our z transformation here. All right, so m naught greater than 75 is going to be the probability of a variable z being greater than, again, it's my variable minus mu divided by sigma. Okay, so that's where all these values are coming from. So 75 minus 50 over 10.31 tells me I'm looking for the probability of my standard random variable z being greater than 2.42. All right, and so thus to get to a the z, because again, remember our z tables are always set up so that we were doing a less than or equal to z dimension. Okay, that's why I got to just switch it to get to a greater than. So the probability that we exceed 75 is 1 minus this phi, which will come out of the standard normal table of 2.42. Well, that value is 0.9922. Okay, and then 1 minus that number gives me a probability of exceeding 75 on the order of 0.0078. All right, so it's less than 1% on this. Okay, now, if we kind of apply this and kind of relate this back to structures, okay, our safety factor is 75 divided by 50, or 1.5, right? This is the load that we designed for. This is what's actually on it, or what we expect. That's our safety factor. In a lot of codes, let's go through, and those of you that have taken steel or concrete, you'll recognize the live load factor of 1.6. Okay, and this is one of the largest safety factors that they use in these load combinations in these design codes. Well, a 1.6 corresponds to an 80, right? If I put a 1.6 here and multiply by 50, I get 80. So let's just see what that probability is. If this is good enough for design, it's probability of our moment greater than 80. If you repeat the process, your z goes to 2.91, okay? And then my probability then of being exceeding this value is 0.0018, right? So what that corresponds to is a number of about 99.8% of the time you will not exceed that value. And that's pretty close to 100. Now, there's some other things and some things that we do to make sure that we still have the safety we need, but that's a pretty high probability that you're going to be less than that number. And so it's kind of interesting that that's where that value starts to come from, is from a statistical analysis of a simple statics problem like this, that they say a live load, which is a load that can have high variability, it's not constant, has high sigma, that they can calculate that quantity. Now, for other types of loads that are more permanent, like dead loads or something, your sigma would be something smaller, and you would have to include that as well. But this is just for a pure live load analysis case, it's interesting to see that number show up. Okay, so anyway, I always find that kind of interesting. This is one of my favorite problems in this series. Okay, just because it kind of justifies a lot of what we do as professional structural engineers. Okay, but it also illustrates the point. Now, that being said, as a designer, you won't be running linear combinations and probabilities. You'll be following design codes, but behind the scenes, that's what's going on. All right. So now, if we look at our next case, let's take a look at what happens if all of a sudden, instead of A1 and A2 being constant, they are now also random variables. Okay, so now we've got 4 random variables in this situation. We have an expected value of A1 being at 5 feet, but now it's got some variability of 0.5 feet or 6 inches. So it could move anywhere on that beam, plus or minus 6 inches. Okay, and then the expected value of A2 is 10 feet, and then it has a standard deviation also of 6 inches. So there's a little bit, and we're not quite sure where this load's going to land. And believe it or not, that happens a lot in practice. Okay, a lot of times we may have some questions on the location of where a load is applied. I know generally where it's going to be, but this is kind of a way to kind of look and see what the effect of this variance is. Okay, all right, so we're going to repeat the process. We're going to look for the expected value of m naught, and we're going to find the variance of m naught. Okay, and we are also going to make the assumption that x1, x2, a1, and a2 are all independent. Now, I left them called as x1. You could have just as easily called this as x3, this is x4. Okay, they're still random variables. Okay, so how you label them isn't a big deal on what we're doing. Okay, but for us, we're just going to work this way. So if we go back to our basic definition, okay, the expected value of a function of 4 random variables, a1, a2, x1, x2, would be equal to, in this case, because I have 4 variables, I now have 4 integrals. I mean, how often do you see that from 4 integrals? Okay, of my function dotted into the probability density function, that PDF, if you will, of a1, a2, x1, x2, as we start to do this, all right? So if I kind of plug in some pieces on this, okay, a couple of things about it. My function is the equation for the moment, a1, x1 plus a2, x2, all right? So that's no problem, okay? And then my f, a1, fa2, fx1, fx2, I can split those guys out if we make the assumption that they're independent, which we did, that all of them are independent. And so then we can say, well, if they're independent, then I can calculate the probability of the intersection of all 4 of these events as just being simply the probability of each one of those multiplied into the other. Okay, and so that's the heart of what we're doing. So we're going back to intersections and unions as we start to look at this. All right, so, and then of course I got to have dx1, dx2, da1, da2 as my references for integration on here. Okay, all right, okay, now, if we do a little bit of algebra and do some expanding, I can rewrite this whole mess up here then as just simply being the single integral of a1 times fa1 da1 times the integral of x1 times fx1 dx1. Okay, so if you look, things can start getting collected. Everything in here is an a1, and it's independent of everything else. Everything in here is an x1, so that's the first part of my equation, plus then the integral of a2 times fa2 da2 multiplied by the integral of x2 fx2 dx2. So the same thing, and if I look at these, I recognize these terms simply as being the expected value of a1 times the expected value of x1 plus the expected value of a2 times the expected value of x2 is the way that all that shakes out. And that's kind of good news because that's the way we would want to be able to do this. So if we go back and we look at our linear combination, we'll start kind of combining these things. All right, if everything is independent on there and you have your linear combination, all you have to do to calculate this combination is take the expected value, basically put a parenthesis around every variable and say I want the expected value of that quantity, and so a1 goes times x1's expected value and a2 goes times x2's expected value. You can just kind of build these things. You don't have to go through that quadruple or more integral, if you will, and to look at it. Okay? All right. So then if we do that then, so that's my expected value of my moment. Okay, and if we do the calculation on this, well, it's the exact same formula. It's still 50 kip feet is the expected value. It's the same as before. Okay, but what changes is the variance. Okay, so if you remember, for variance of a random variable, we take the expected value of my random variable squared minus the expected value of my random variable, that whole quantity squared. That was our shortcut formula from before. Okay, so we've got the second term already. Okay, that was this 50 that's happening up here. Okay, and then so for my expected value of m naught squared, then all I'm doing is I'm now squaring the terms associated with this. And so again, saving you a little bit of the algebra involved, we get a formula like something kind of like this. Okay, and so if I go through and I collect all these terms, and then if I take the expected value of this guy minus, where'd it go? This guy squared, I will get a formula that looks something like this. All right, expected value of a1 squared times the expected value of x1 squared minus the expected value squared of a1 times the expected value squared of x1 plus the expected value of a2 squared times expected value of x2 squared. Okay, minus the expected value squared of a2 times expected value squared of x2 squared. So you can kind of see it's following that same kind of pattern about putting things into x squareds and xy's as we talked about last time. All right, so then if I plug the values in, my variance is now 111.56, okay, and that's up from, what was my number before? 106.25, so it hasn't moved a whole lot on there. It did move a little bit, so that will make a difference on my probability of things as things start to move around. Okay. Okay, now, so, and then you could go find probabilities the exact same way if they're independent. Okay, now let's go ramp it up a notch here. All right, and the last piece that we're going to look at then is let's repeat the probability calculation that we just did. Okay, except now a1 and a2 are constant again. So a1 and a2 are constant with the same values as before. Okay, and x1 and x2 are no longer independent. Okay, but rather they have a covariance between them in the amount of 0.5. Okay, all right, now the expected value is what we expected it to be. It's still 50 the 50 kip feet, so we don't need to go through that again, but the variance formula changes a little bit, and this one gets a little wonky on this. Okay, so again, we're going to go back to our formula of expected value of m naught squared minus the expected value of m naught quantity squared to calculate the variance. Okay, so I have this one, that's my 50 squared. Okay, it's this guy that we got to calculate, so we're going to do a little bit of algebra on this. Okay. In fact, I've actually written all of these terms out again for us, that the expected value of m naught squared is the expected value of this big thing. Okay, and again, if we have a linear dependence, then I can't just drop out anytime I take these guys multiplied by each other. Okay, and so your formula ends up looking something like what we had before, this guy and this guy, but now I also pick up this term on the end, 2a1a2 times the expected value of x1 times x2. Okay, and then if I repeat the process for the expected value of m naught, I get the same two first terms that I had, but then I also get 2a1a2 times the expected value of x1 times the expected value of x2. Okay? All right, so if I put all these together, and again, it's just a lot of algebra at this point, so like I say, if you need to pause the video and kind of follow through on the math, or you can just take my word that the algebra is right, and I hope it is, okay, but we can kind of look at this. So if I put all these pieces together where I take what I would call as equation 1 and equation 2, and I take 1 and I subtract 2 from it, there, okay, this is big monster is what I get. And so what you see in this is that if I collect all the terms, I collect all the a1 squared terms, I get an expected value of x1 squared minus expected value squared of x1. Well, that looks familiar. That looks like the variance of x1. Okay, and likewise, the expected value of x2 squared minus the expected value squared of x2, that's the variance 2 calculation that comes out of the algebra that we just did up there. Okay, the difference is the last term, 2a1a2, I get the expected value of x1 times x2 minus the expected value of x1 times expected value of x2. That guy right there is a covariance. Okay, if you remember our definition of it. So my variance of m naught then is everything that I had before plus this last term, 2a1a2 times the covariance of x1, x2. Okay? All right, so now I can kind of plug these pieces in, and I can get my variance of m naught is going to be equal to 25 times 0.25, so that's 5 squared. This is 0.5 squared. Okay, and then this is 10 squared, and then this is 1 squared, plus 2 times 5 times 10 times my covariance of 0.5. And if I do that, now my variance is now 156.25. It's really jumped up. Okay, and that's because there was an interdependence happening on x1 and x2. Okay, if I look at my standard deviation of this by taking the square root of that value, we get a value of 12.5 kips per foot. Okay, so let's go back and let's check our probability of m naught greater than 75. Okay, same process. Okay, except now the only thing that's changed is that number in the bottom has moved. Okay, so before we were at a number that was, what, 2.42 before. Okay, when I run through this transformation, I'm now at z equal to 2.0. So before, when they weren't independent, you were out looking at this, but now I'm looking at a band that's been moved in a little bit, okay? That z value has moved quite a bit. Or if you look at just the one side of it, it'll probably make a little bit more sense. That we were here at 2.42, and now, because they're interrelated, we're now at 2.0. And we're trying to calculate that area. Okay, and so now it becomes 1 minus the of z less than or equal to 2.0 is now equal to 1 minus 0.9772, okay, which gives me a probability of about 2.3% that will exceed that, okay? And so that becomes kind of a dangerous situation. I wouldn't want to go into a building when 2 times out of 100 it fails, right? That would not be a good situation. So as structural engineers, these probabilities and these statistics are very, very important to the way that we assign our safety factors and our confidence in what it is that we're trying to calculate, and in this case, protecting the public based on our moments. Okay, now, like I say, I don't want to scare anybody and think that every building you walk into is designed at this limit. There are a lot of other safety factors and precautions that are built in that most buildings will never see these design loads that were happening. But in order to be able to do probability and in order to have confidence, which is what we're going to start talking about in the next couple of videos, we have to know the parameters that help us to define those. Okay, and so that's all we're kind of looking at on this. So now we're at 2.28%, and before we were less than 1%. Okay, and all because there was this covariance that existed between x1 and x2 on this. So I also thought this problem was kind of interesting and kind of showed how the numbers can move from a statistics standpoint. So I hope that made sense to you. Like, as always, if you got any questions, leave me some feedback down below in the comments. Okay, and as always, be sure to like the video, and if you would, subscribe to the channel. That'll help us out quite a bit. So anyway, you all have a wonderful evening, and I will see you next time. Happy engineering.